ধন্যবাদ সবাইকে। আজকের এই ওয়েবিনার, আমাদের আজকের স্পিকার হচ্ছেন স্বপ্নীল শয়ন সাহা। সে হচ্ছে পিএইচডি ক্যান্ডিডেট, ইউসিএলএ ইউনিভার্সিটি অফ ক্যালিফোর্নিয়া, লস অ্যাঞ্জেলস, আন্ডার প্রফেসর, বিখ্যাত প্রফেসর প্রফেসর মানি শ্রীবাস্তবা। তো টপিক হচ্ছে এআই এনেবলড আইওটি ইন্টারফেসেস, সরি, ইনফারেন্সেস ফ্রম সেন্সর ডাটা ফর টাইম ক্রিটিক্যাল অ্যাপ্লিকেশনস। আমার বাচ্চা আমাকে ডিস্টার্ব করতেছে, ফলে খুবই ডিফিকাল্ট হচ্ছে। তো এখন যেটা সেটা হচ্ছে যে স্বপ্নিল আমাদের ঢাকা ইউনিভার্সিটির টিউটোরিয়াল ডিপার্টমেন্টের স্টুডেন্ট ছিলেন এবং এখন পিএইচডি করছেন এবং অসম্ভব ভালো কাজ করছেন। অলরেডি কয়েকটা অ্যাওয়ার্ড পেয়ে গেছে পিএইচডি তে, এর আগেও অনেক অ্যাওয়ার্ড পেয়েছিল এবং আমরা আশা করি যে মানে ইউল বি এক্সেলেন্ট। অতীতেও আমাদের বিভিন্ন ওয়েবিনারে তিনি বক্তব্য দিয়েছেন এবং আমরা খুবই উজ্জীবিত যে আহ, উনি আমাদের জন্য সময় বের করেছেন এবং হি ইজ এ ভেরি গুড স্পিকার উইদাউট ডাউট, এবং যথেষ্ট নলেজ নিয়ে কথা বলে। আমরা সবাই চেষ্টা করব যে টকটা এনজয় করতে, এবং এটা রেকর্ডেড হচ্ছে এবং আমরা পরবর্তীতে শেয়ার করব। ধন্যবাদ স্বপ্নিল, প্লিজ স্টার্ট। থ্যাংক ইউ সো মাচ।
Yeah, thanks a lot, sir. Uh, okay, let's start. So, as Adsar mentioned, so আজকে টক হচ্ছে কিভাবে মেশিন লার্নিং আইওটি সিস্টেম সেট অ্যাপ্লাই করা যায়। বেসিক্যালি মেশিন লার্নিং তো আমরা কম্পিউটার্স বা সার্ভার্সে ইউজুয়ালি ট্রেন করি, রান করি। But recently there's been a push to run these models on IoT devices. So that's what we're going to বেসিক্যালি যদি আমাদের সেন্সর ডেটা থাকে, কোনো আইওটি ডিভাইস যদি সেন্সর ডেটা কালেক্ট করে, দেন হাউ উই আর গোয়িং টু রান মেশিন লার্নিং অন দ্যাট আইওটি ডিভাইস and do inference on the device. So that's the topic of the talk. Okay, so আমি বেসিক্যালি ফোকাস করবো IMU সেন্সর নিয়ে, and it stems from the fact that I've been working on it since my undergrad days with Ahad sir. It's pretty interesting, IMU sensors, because you can do a lot with it. So basically, we have IMU sensors everywhere. So IMU basically consists of accelerometer, gyroscope, and magnetometer. So accelerometer measures the specific force of the object, gyroscope measures the angular velocity, and magnetometer measures the heading. So এই তিনটা sensor use করে, obviously using AI as well, you can do a lot of stuff. So people are using inertial sensors in autonomous vehicles and drones for estimating orientation, estimating location. But just beyond this, আমাদের পকেটেও we have IMU sensors. Like আমাদের যে smartphones বা smartwatch আছে, even iPads, laptops, televisions, we have inertial sensors in them. Like আমরা যখন একটা ফোন, like if we hold the phone vertically and then যদি আমরা ফোনটাকে ঘোরাই, then the screen also rotates. That's possible due to inertial sensors. Beyond that, recently যেসব রোবট আছে মার্কেটে যেগুলো বাসা ভ্যাকুম করে, they also have inertial sensors to make sure that the robot is flat. And এছাড়া স্মার্ট হোমে কন্টেক্সট ডিটেকশন, অগমেন্টেড রিয়ালিটিতে object placement, so these sort of things need image sensors. And as I've mentioned, a lot of this has been possible because we are using neural networks. তো যেটা আমরা করি, আমরা র অ্যাক্সেলেরোমিটার, জাইরো, ম্যাগনেটোমিটার ডেটা একটা নিউরাল নেটওয়ার্কে দেই। Then we have the labels for the kind of inference we want to make. Like আমরা যদি activity detection করতে চাই, then we are gonna have activity labels. And then we train the network to predict those labels. So this is how people have been sort of doing processing from inertial sensor data using neural networks. Now, recently another thing has been coming up, এখন এটার নাম হচ্ছে AI enabled IoT. So AI enabled IoT, the reason that AI enabled IoT has come up is because we want to make complex inferences but on device. Now এখন অনেকগুলো applications আছে যেখানে typically you won't have a server or a laptop. Like for example, if you look at autonomous cars, you have to take images and make all the decisions on board in few microseconds. So ওই টাইপের application, it's very hard to offload your data to a server, run inference, and then bring back the decision, because you're gonna waste a lot of time. So those type of applications are known as time critical applications. And there are other applications which is known as remote applications, where you might not have internet access. Like if you're doing wildlife monitoring, or if you're doing search and rescue in remote mountains, then internet power obviously on a tough. So that time, if you want to use some AI to make some inference in the field, then you really cannot upload the data to a cloud and then do inference. So এখানে কিছু example applications এর photos দেওয়া আছে. So these are the kind of applications যেখানে if you want to use machine learning, it's best to do it within the device, because you cannot really afford the delay that it takes to upload the data to the cloud and then bring back the results. So this field emerged to make complex inferences for time critical and remote applications, which is the topic of our talk. Now the problem is neural network আর কি, তো আমরা সবাই পাইথন বা ম্যাটল্যাবে ট্রেন করে we get some nice results and we just say okay, we're done. But actually it's very hard to deploy these networks. And the reason is networks are becoming more and more complex. Like যখন 2012 এ first deep learning revolution start হয়, then we started with a neural network called AlexNet, right, which was a simple convolutional network. But we have come a lot further than that, right? So after AlexNet, we had VGG, we had Inception, then for mobile phones, we had MobileNet, we had ShuffleNet, and now we are in the era of transformers, right? So we have large transformers like GPT-3, BERT, যেগুলো আর কি unlevel data থেকে they can create a lot of insights. So these networks are very complicated and quite heavy. So as you can see in the first chart, you can see the number of parameters of these networks is increasing day by day. However, the problem is like Moore's law can go so far, right? Like we can pack so many transistors in a chip, and are able to run all these networks. So we know that Moore's law is sort of coming to an end. So it's very hard to keep up with changes in software that happen, right? So hardware development that fast chana. It takes time to reduce the size of the transistor and then push the hardware to the market. But software, it's just evolving every day. So what happened was there's a gap. So basically, neural networks are becoming more complex. Kintu amader je shob like IoT platforms gulo ache, they're becoming smaller and smaller and smaller. So they are becoming smaller not just in terms of processing power, but in terms of communication bandwidth and energy budget as well. So how will you run neural networks if this trend continues? So that is the main challenge, and to solve that, people have been trying to work on it since 2017. And what they are trying to do is they have created some tools that can allow you to explore, optimize, and integrate neural networks on IoT platforms. So I'm going to explain what explore, optimize, integrate is. The problem is they are not doing it for real life applications in a platform aware fashion. So what I mean by that is, so this is the IoT pipeline that exists today. So normally what you do is you pick a data set, then you extract some features optionally, and you pick some models from an efficient model zoo. So when you think of neural networks, আমরা চিন্তা করি CNNs, LSTMs, but there are models beyond that I'm going to show. So pick one of the models from it, and then typically we design the model ourselves, but that is not how it works in IoT, because humans are bad at designing stuff. So we let something known as neural or model architecture search design the network for us. That's known as optimization. And then আমরা Python modelটাকে C তে convert করি using some compiler, and then we load it onto sensors and microcontrollers. So this is how things have been since people first started looking into this problem in 2015. Problem is you're gonna see people are doing a lot of toy problems, like detecting cats and dogs, detecting anomalies, those kind of stuff. Like if you really want to do complicated stuff on microcontrollers, people have not really explored it until now. And the reason people could not do it is people don't think in a platform aware manner. So what I mean by platform aware is when you are designing your neural network or your model through this pipeline, it must have some idea about the capabilities of the target device you're going to run your model on. So that means যে আমাদের মাইক্রোকন্ট্রোলারের কিছু RAM, flash constraints থাকবে, it's gonna have some energy budget. So they have to be fed somehow into your design, like this entire pipeline that you see. So that thing was not there. Plus, there are ways to make small networks do even more. So those ways have not yet been explored. So that's where my research comes in. So আমি রিসার্চে যেটা এক্সপ্লোর করি সেটা হচ্ছে যে we have a lot of inertial sensors around us, and there are a lot of bunch of other sensors too, like microphones, thermal sensors, and so on. So এইসব সেন্সর ইউজ করে আমরা কিভাবে রিচ অ্যান্ড রোবাস্ট ইনফারেন্স নিয়ে আসতে পারি to the user on board, on device. Like we're gonna have a neural network that runs on device, and then this is gonna give the user some type of rich or robust inference, like complex event processing or localization service and so on. Now there are a few challenges. Particularly, what I mean by robust is time series data. When you collect sensor data in the field, they're very noisy. There's a lot of uncertainty in it. So when you are designing your neural network, it must be aware of these uncertainties. Okay, so there are sensing and timing uncertainties that I'm going to show. So if you don't make your network robust to these uncertainties, then it's going to perform poorly. Okay. And what I mean by platform aware, I've already said যে আমাদের যে ডিভাইসটা থাকবে আমাদের সেই ডিভাইসটার যেসব constraints আছে. So our model development pipeline must be aware of those, like RAM, flash, any kind of compiler dependencies. Like you cannot just take a random model and compile it for a microcontroller. So compiler কিছু restrictions আছে. It cannot use every possible way. So that's known as platform aware, that it must have the proper hardware and software formulation for exploiting full device capabilities. And we are focusing on low-end devices. What I mean by low-end is obviously there are high-end IoT devices also, like Raspberry Pi and Jetson Nano, but I'm not really interested in those because they are quite powerful. They're similar to computers now. What I focus on is low-end microcontrollers and sensors. So these devices typically have just a few hundreds of kilobytes of RAM, around 1 megabyte of flash, and they have less than 1 watt of power. So they're constrained in power, they're constrained in memory. They typically have single core and they run on battery. So you have to take into account these things when you are developing your model. And what I mean by rich as well as intelligent is whatever output your model is giving, it should be multi-class, it should be context aware of the surroundings it's operating in. And the problem should be such that it's sort of non-interpretable. What I mean by that is, sure, machine learning ছাড়াও অনেক কিছুই solve করা যায়, but the problem should be such that it's very hard to do it without ML. So it must be worthy to apply ML to it. So normally I have seen people applying machine learning to everything. That's not how we do things when you are trying to run on microcontrollers. So if we don't need ML, we don't use ML. Okay. So we only consider problems where ML is worthy to investigate. Are there any questions so far? Okay.
কোশ্চেন নাই। তুমি যদি যে একটু ইয়া ব্যবহার করতে পারো, কার্সার,
Okay.
তাহলে ইজি হয় আর কি। থ্যাংক ইউ।
Okay.
সুন্দর।
Okay, so let's take a look at all of this step by step. Okay, so we have a few design principles that we use to fulfill all these requirements. So firstly, let's take a look at how we can make robust inferences. So যখন আমরা ফিল্ডে সেন্সর ডেটা কালেক্ট করি, then we face some issues. Okay, first issue that we face is something known as sampling rate jitter. So sampling rate jitter যেটা হয় যে আমরা যখন সেন্সর ডেটা কালেক্ট করি and আমরা যখন উইন্ডোইং করি, we expect the sampling rate to be constant, but that is always not the case because of packet drops, because of scheduling errors and the microcontroller. So আমরা যে ডেটাটা পাবো, if you look at the timestamps, you'll see that it's not like the timestamps don't have a constant difference. So there is a sampling rate difference that happens. So আমরা যখন উইন্ডোইং করব, if we want to window at constant time and not samples, then we're gonna see something like this, যে আমাদের একটা উইন্ডোতে 4টা স্যাম্পল আর বাকি উইন্ডোতে 3টা স্যাম্পল, তো কম বেশি থাকবে আর কি স্যাম্পল. So this is not good, because what might happen in the field is if your sampling rate drops suddenly, then your neural network performance will drop as well. Okay, or if the sampling rate rises too much. So আমাদের neural networkকে aware করতে হবে যে in the field this problem might exist. And the way we do that is by applying something known as adding artificial jitter in sampling rate. সো আমরা যেটা করি যে উইন্ডো সাইজটা আমরা টাইমে না করে আমরা উইন্ডোটা হচ্ছে স্যাম্পল লেভেলে করি, অ্যাজিউমিং উই মেক আ স্মল অ্যাজাম্পশন দ্যাট আমাদের যে জিটার আছে ইট ইজ উইদিন সাম বাউন্ডস, অ্যান্ড দেন উই হোয়াট হ্যাপেন্স বাই ডুইং দ্যাট ইজ আমাদের যে টাইম লেভেলটা আছে, সো উই হ্যাভ সাম jitter in the time, right? Plus minus delta t1 plus minus delta t2. So my time is varying, but my samples in each time window is constant. Okay. So this actually helps, if you just take number of samples, and it seems like a very, I guess, naive way to solve things, right? But what will happen if this time is also wrong? Like আমরা তো এখানে একটা বড় জিনিস assume করতেছি যে আমার time stamp correct, but what if my time is wrong as well? So that can happen when you are doing multimodal fusion. You are collecting data from various sensors. Then যেটা হতে পারে যে since sensors run at different sampling rates and they observe things at different times, so আমি যে ডেটাটা পাবো সেই ডেটাটা I can't just assume that they're coming at the same time from two sensors. There might be a small gap between the first sample of sensor 1 and the first sample of sensor 2. So what we do is we add artificial misalignments. So আমরা ট্রেনিং টাইমে এরকম যে গ্যাপটা আছে, so we add these gaps in every time window. Okay. So by doing that, we're making the neural network aware that basically we're making the neural network robust to this sort of timestamp gaps, because if we artificially do it, it acts like data augmentation, and then during training time the network learns that there might be some sort of error in the first samples of each sensor. I should probably consider them together. So both these approaches, they use data augmentation. Now the third issue which is related to something like jitter and timing errors, is the issue of missing data. So in missing data, what happens is if you assume that your time is good and you are sampling at a constant rate, and then what might happen is you might have some samples that are missing in each window. Like here we have 4 samples in the first window, and the next we have 2, and then in the next we have 3. So there are a few ways to solve it. The first way that we solve it is using something known as masked channel. So assuming that your clock is good and there is no timing error, then you can use a binary mask to signify where the data is missing. Okay. So that tells the neural network to ignore those data points during training. However, if your time is not good, as we showed that there might be some jitter and timing errors, then what we do is we push this containing samples at the start of the window, as you can see in window 2 and window 3, and then we replace the missing samples with some number that is not inside the typical distribution of the data. So once you do that, then the network learns that there is something wrong with this number, so it should probably not consider that during training. Okay. So these are some of the techniques that we use to handle these 3 issues in the field, and they are quite prevalent. If you look at open data sets, you will see that the timing doesn't match. There is some jitter in sampling rate, and you will see that there are obviously some missing data in the data sets. So আমরা অনেক অ্যাজিউম করে নেই যে নিউরাল নেটওয়ার্ক তো এগুলো শিখেই ফেলবে, তাই না? But we found out that is not the case. It does not learn by itself to handle this. So what you see here is local benchmark. So what we did was we trained normal neural network to do complex event detection, and then we did not include these three changes that we just proposed. And then you can see that it actually does pretty poorly when it's trying to detect the micro events in a complex event, like only 48% accuracy. Normalization interpolation, it also doesn't seem to help that much because normalization interpolation assumes there is no timing error or some limit error, but there is, those errors present. However, when you start adding, you know, the augmentation approaches that we showed, you can see that the accuracy starts to improve. So microactivity recognition jumps to 72%. And once you include everything, then my macroactivity recognition also improves to 88%. So by using these three approaches with a neural network, you can get anywhere from 11 to 24% accuracy improvement over a neural network that is not aware of these things. So this proves that it's helpful for the network to be aware of uncertainties. And we also have global benchmarks. So এই পেপারটা একটা কম্পিটিশনের পার্ট ছিল, and our pipeline was the best deep learning based pipeline, and it did not require relabeling. So what a lot of people will do in complex events is ওরা ground truth দেখে manually relabel করবে data to handle all the uncertainties in the data, but we don't need that because our framework learns to do it automatically during training, and it's the only framework that is uncertainty aware among all of the other computing methods that were submitted to this competition. So we did pretty good without any human effort, that I can say. Okay, so do we have any questions so far? Okay, if not, then we can move on to our second topic, how to do platform aware machine learning. So normally when we train a model, আমাদের একটাই goal থাকে accuracy maximize করা, but that's not what we do in IoT systems. So IoT systems আমাদের goal থাকে যে আমরা error বা accuracy maximize করব, error minimize করব, accuracy maximize করব. But also we will have to take care of latency, flash, SRAM, and obviously if you have other things like energy budget and those things, so they should also come in this optimization function. So আমাদের goal হচ্ছে we want a model that has the lowest error, lowest latency, but that has flash and RAM uses that is less than the limits of your microcontroller or sensor. And এখানে যে সিগমাটা দেখা যাচ্ছে in the equation, the sigma is known as my neural network search space. Okay, so suppose if I have a CNN, then একটা CNN এর কি search parameters থাকতে পারে, number of layers, the size of the kernel, type of activation to use. So those are known as my neural network search space. And this lambda that we see in the equation, these are weighing parameters. So our goal হচ্ছে আমি এই optimization functionটা somehow solve করতে চাই given flash, RAM, and latency constraints. So now how do we get each of these terms? So my error I can easily get from the validation loss, right? So I will pick a random model from the search space, I will construct it, then I'll try to see what my validation loss is, right, of that certain candidate model. Now how do we get the flash? So there are two ways to do it. আমাদের কাছে যদি আমাদের microcontroller like Arduino or STM32 already থাকে, we can plug that into our GPU machine or a laptop, and then we have this framework which can automatically communicate with that hardware during runtime to see if a randomly constructed model fits within the device or not. So that's one way to do it. If you don't have that information, like which we call hardware in the loop information, then you can use some analytical formula to do it. Like আমরা যেটা করি, আমরা মডেলটাকে TensorFlow লাইটে কনভার্ট করে দেন দেখি যে ওটার ডিস্কে ওটার সাইজ কি. That gives us a good idea actually how much flash our model might use on a device. We do something similar for SRAM. আমাদের যদি actual microcontroller থাকে, then we can get it directly from the microcontroller. But যদি না থাকে microcontroller, then we use this analytical formula যেটা হচ্ছে আমার per layer maximum activation size কত সেটা calculate করা try করে. This works okay for a few types of models, but we'll show that actually harder in the loop হার্ডওয়্যারটা সাথে রাখা ভালো আর কি। ইউ গেট লাইক আ মোর স্ট্রঙ্গার গ্যারান্টি যে আমার মডেলটা রান করবে ডিভাইসে। And finally, we have latency. So typically people use something known as floating point operations per second as a proxy for latency, but that only works if you are optimizing convolutional models. আমার যদি recurrent models বা transformers বা there are special models আরো আছে যেটা দেখাবো, ওগুলো থাকে, then this will not really work. Then you need the actual latency information from the target hardware. Sir, I think you raised
হ্যাঁ
your
হ্যাঁ
question.
আচ্ছা, থ্যাংক ইউ সো মাচ। আমার প্রশ্ন হচ্ছে যে এখানে অনেকগুলোই তো ভেরিয়েবলস আমরা দেখতেছি, তো এই সবগুলো ভেরিয়েবলের কোনগুলো আমরা অ্যাজাম্পশন করে নিচ্ছি কোন একটা ভ্যালু, আর কোনগুলো আমরা মানে একদম ডিরেক্ট নিউমেরিক্যাল ভ্যালু পাচ্ছি, বা এরকম কিছু আছে, বা বা কোনো কিছু অ্যাডাপটিভ বা কোনো কিছু ফিক্স, বা কোনটা বেশি ইম্পর্টেন্স এখানে এরকম?
Are you talking about this lambda weighing parameters or the values themselves?
ভ্যালুজ ইটসেলফ, লাইক এই যে ল্যামডাটা অবশ্যই, প্লাস হচ্ছে যে বিভিন্ন মানে যে অ্যাপ এরো বা অ্যাপ ফ্ল্যাশ সেগুলো যে বেরোচ্ছে মানে বের করছি, এর মধ্যে যে যে ইনফরমেশন কিছু তুমি বলেছো যে কিভাবে বের করতে হয়, কিন্তু এখানে আহ, কোন জিনিসগুলো আহ, মানে যেমন ফ্লপস ভ্যালু ফর এক্সাম্পল, ওইটা কি আমরা ওখান থেকেই পাচ্ছি, বা লেটেন্সি যে ইনফরমেশন সেটা আমরা কি কোনো কিছু অ্যাজাম্পশন করে নেই যে এরকম একটা ভ্যালু হবে, নাকি আমরা একসেপ্ট করতে হবে? যেহেতু আমি এই ডোমেনের না একদম, এই জন্য
No, we like people. There are papers that assume stuff, but I don't like to assume things. So I normally get my information directly from the microcontroller.
আচ্ছা।
Uh, but there are ways to also calculate them analytically. Like as I said, Flash. আমরা যেটা observe করছি যে if you convert a model from Python to TensorFlow-Lite, then it gives a good idea of how much flash your model might consume. But that's just an approximation. That's not the exact thing. Same for flops or SRAM analytical formula. So yeah,
Okay.
these are all calculated during runtime. You don't really assume anything. The only thing that you need to specify are these lambdas to weigh stuff. So how much weight you want to put on, for example, the accuracy of your model versus flash RAM or latency. So the sum of these lambdas is obviously is going to be 1 because it's a weighing parameter. But otherwise, yeah, we don't really assume stuff.
আচ্ছা, ঠিক আছে, থ্যাংক ইউ।
এখন কথা হচ্ছে আমি তো বলতেছি যে we can randomly pick a model, but we don't do that because random sampling takes a long time if you have a large search space. So we do intelligent searching. Okay. So what we specifically do is known as Bayesian optimization. So what happens in Bayesian optimization is আমার যদি একটা সার্চ স্পেস থাকে অ্যান্ড আমরা যদি সার্চ স্পেস সিগমাটাকে আমার একটা ফাংশনের ইনপুট চিন্তা করি বা ডোমেন চিন্তা করি, then my f opt is gonna be my output, right? So it's gonna be my y. And what Bayesian optimization tries to do is based on the domain sigma. It tries to approximate the value of f opt with as little sampling as possible. The way it does this, it uses something known as the Gaussian process. So Gaussian process যেটা করে সেটা হচ্ছে আমার যদি সাপোজ আমার f opt হচ্ছে জাস্ট দুইটা পিক, okay. So if it is two peak, then I can approximate it using a two peak normal distribution, right? So bimodal normal distribution. So Gaussian process tries to approximate f opt versus sigma using multimodal normal distribution. Okay. So that works fine for a lot of different search spaces. And to construct it, আমার তো এখন কিছু data points দরকার, right? So I have to choose some values of sigma and then have to see how f opt varies. এখন random sampling করলে is gonna take a long time, so we don't do random sampling. What instead we do is something known as Monte Carlo sampling with upper confidence bound. So Monte Carlo sampling with upper confidence bound যেটা হয় যে আমি first 2-3 epochs I'm gonna do random sampling. আমার হচ্ছে f opt এর একটা রাফ আইডিয়া আসবে যে f opt দেখতে কিরকম হবে versus sigma. Then I start doing something known as exploration and exploitation. So if you have done reinforcement learning, then it is very well known. So in exploration, you try to use your previous knowledge to improve your results. So that's exploitation, sorry. And in exploration, you try to explore unexplored parts of your search space. Okay, so this type of sampling, as you have seen, it does not use any gradients. So আমরা gradient descent use করি না because a lot of these terms is not really differentiable. Okay, and we have found out that using this approach of Monte Carlo sampling, we can optimize the effort really well within 50 epochs. So আমার মাত্র 50টা মডেল ট্রেন করা লাগবে ক্যান্ডিডেট, অ্যাকচুয়ালি 50টা লাগে না। Once you code this thing really well, you will see that it actually needs to train around 15-20 models to give you the best approximation of effort. Ultimately, what you'll get is you'll get a model that has the lowest error, the lowest latency, and the flash and RAM, they fit within the device constraints. So that's the sort of, you can say, magic that you use to solve this optimization equation. And this is actually what people do in the field. So they use different ways to solve this equation. So I like to use Bayesian optimization. There is also genetic algorithms that does something similar. A lot of people also uses gradient descent itself to solve this. That assumes that your parameters are differentiable. That is always not the case. And then there is also other techniques that people use. Okay, but normally this is how people try to do platform aware machine learning. And this is how it looks like once you implement everything in TensorFlow, PyTorch, Keras, and you have your microcontroller. It's going to look something like this. So আমার দুইটা পার্ট থাকবে। আমার থাকবে হচ্ছে হোস্ট মেশিন, যেখানে আমি আমার মডেলগুলো ট্রেন করব। So it can be your laptop, or it can be Google Colab, or a server, or a GPU workstation, anything like that. And then I'm going to have my microcontroller, which I call the target hardware in this figure. So আমার যে প্ল্যাটফর্ম অ্যাওয়্যার নিউরাল আর্কিটেকচার সার্চটা দেখালাম, সেটা রান হবে জিপিইউ মেশিনে। It's gonna call TensorFlow to train candidate model. So it's gonna pick a model from the design space. It's going to train it. Actually, it's not gonna train it fast. First, it's going to see if it fits or not. So it can do it in two ways, right? So as I said, if you have your target hardware, it's gonna get the information directly from the hardware, the latency and SRAM and flash. But if you don't have this hardware yet, it will use the proxy module, okay, like the approximations that I showed you in the last slide. So it can also use those to get the RAM, the latency, and the flash roughly, okay. And then it tries to do this like around 10 to 50 times, and then it's gonna give you the best model that you can get. Now this part uses Keras and TensorFlow in my implementations. A lot of people also use PyTorch. এখন আমরা যখন মডেলটা লোড করব to test if it fits within the device or not, so I used something known as TensorFlow Lite Micro. So what TensorFlow Lite Micro does is first you train your model in TensorFlow, and then you use TensorFlow Lite converter to convert it to TF Lite, and then you convert it to C using TensorFlow Lite Micro interpreter format. Okay. So once you do that, you're gonna get your if you have coded in Arduino. So in Arduino we have the main file where we have void setup and void loop. Apart from that, you're gonna also have like model.c and model.h. So you load all of those things into your microcontroller. And apart from that, it also loads something known as a model interpreter. So what the interpreter does is it sort of acts like a manager. So it is gonna load your model, it's gonna allocate memory. And it's also going to see what operators you need, like do you need convolutional operators, do you need some specific activations, and so forth. And then it loads the model into the SRAM, okay, and it loads it in a place known as Arena. And once that is done, then you can start to do real-time inference. So for example, here your IMU data is gonna be fed into the model, and your model is going to give you some output. Okay, so this is how it normally looks like, okay, when you are doing platform aware model development. যে আমার হার্ডওয়্যারটা আমার সাথে থাকবে, and আমি টেস্ট করে দেখবো যে একটা সার্টেন মডেল হার্ডওয়্যারে ফিট করে কিনা. If it doesn't fit, then I will use that information to pick a better model. Okay. Okay, do you have any questions so far? Nope. Okay, then we can move on to our last topic, how to make rich inferences. So normally when we design a network, আমরা খুব বেশি চিন্তা ভাবনা করি না যে প্রবলেমটা আসলে কিভাবে ফর্মুলেট করা উচিত। আমরা জাস্ট অ্যাজিউম করি ওকে আমি নিউরাল নেটওয়ার্কের দিকে জাস্ট ডেটা দিয়ে দিলে সে ম্যাজিক্যালি শিখে যাবে সবকিছু। দ্যাট ডাজ নট রিয়েলি হেল্প ওয়েন ইউর মডেল ইজ ভেরি স্মল, বিকজ আমার মডেল যদি ছোট হয় আমার তো খুব বেশি প্যারামিটার্স নাই, তাই না? তো লার্ন করা অনেক, মানে জিনিসপত্র লার্ন করা ইটস প্রিটি ডিফিকাল্ট উইথ লট লেস প্যারামিটার্স। So what my approach is, we feed something known as physics to the model. Okay. So for example, in this equation, what we were trying to do was we're trying to predict the location of an object from raw accelerometer and gyroscope readings. Okay. So normally how people have done it for at least 4 or 5 years is they try to predict the heading and displacement rates, and then they just integrate that to get the position. Okay. So that works fine when your model is very big, but if your model is small, then it does not really learn the relationship between your velocities and the ambient readings. So it becomes very hard for the network to learn. So we try to help the network by making some enhancements. Okay. So first thing we do is we change the formulation. So heading rate and displacement. So displacement rate is very easy to learn, but heading rate is very hard to learn because of singularity. So we say that you don't need to predict this; just predict the x and y velocity. Then I can take care of the rest. Secondly, we feed the network with additional data when we have. Like if we have magnetometer, we start feeding it with magnetometer data. Okay, so additional data helps. And then we feed the network with also some physics information. Like for example, a step counter or output of an activity detector, something like that. So these sort of things actually helps. If you look at our paper, we have shown that properly formulating the problem, supplying more data, and also adding some information about the rules or the physics or the bounds that the network must follow. So it helps the network's error to be lower. So problem formulation is very important when you're trying to do something complicated on device. And we actually do something similar. So those of you who are in robotics, you have heard of Kalman filters or Ph.D controllers. So those you have to give a very nice system model to them in order for them to work. The problem is it's very hard to model real systems. So what we do is we let a neural network model the system. So in this case, what we're trying to do is get the position and velocity from GPS and IMU. So obviously this is not a very hard problem, right? So people have done it. But the problem that does happen is they tend to rely too much on the GPS rather than the IMU. So to prevent that from happening, we train the network to predict very accurate velocities from IMU and physics channels. And then occasionally we collect GPS measurements and we update our position and velocity. So we call this neural Kalman sensor fusion, where your system model is a neural network and your measurement is coming from your normal GPS or any position service, something like that. So by wrapping the network in some sort of well formalized human design filters or rules or problem formulation, you can do a lot more out of the neural network than if you just throw the data at the network and expect it to learn. Okay, so problem formulation is very important when you're trying to deploy models to IoT devices. And the next thing that's important to do is not just blindly choosing CNNs, LSTMs, or transformers. Okay, sure, transformers are now the state of the art, but transformers echono you cannot run them on microcontrollers, like they're very heavy. So there are these special classes of models that have been specifically designed to run on microcontrollers. Okay, so a good example is lightweight decision trees and lightweight cannons. Okay, so what they do is so if you have your data, so it's obviously going to be very sparse and it's going to be in very high dimension. So it learns the projection matrix during training time, and then it projects it into a low dimensional space where you can see the boundary between two classes are linear. Okay, so once you do this sort of projection, then you're not going to need a very complex tree or a complex KNN to learn the pattern here. So this actually helps you get a very light decision tree and canon that you can deploy on microcontrollers. So people use this sort of trees and canons a lot when trying to deploy models on microcontrollers. Going beyond that, if you want to move into the neural network space, and suppose you want to deploy LSTMs on microcontrollers, so LSTMs are pretty heavy, right? So lightweight version of LSTM is obviously the normal recurrent neural network RNN, but the reason we don't use the normal RNN is because it has the exploding and vanishing gradient problem. So what people have done is they've taken the RNN architecture and they tried to solve the exploding and vanishing gradient problem with it. The way they did it is two ways. So firstly, they added a scalar parameter here, which you see it's a very complicated term. So by adding that, they showed that, okay, now my model is very stable. It doesn't have the exploding and vanishing gradient problem. Then next, to emulate the behavior of LSTM, they've added this entire non-linearity block here. Okay. So in normal in LSTM, what happens is you have your past states as U and you have your current inputs as W, and then you feed it through the tan H and sigmoid and get a non-linearity to get your current state. Okay. So they've created a lightweight version of it where your U and W are low rank, sparse, and quantized. So in this way, you can actually deploy LSTMs on microcontrollers. And then if you want to deploy, suppose CNN LSTMs, convolutional LSTMs, then you can use something known as temporal convolutional network. So temporal convolutional network, its specialty is it can do the job of both CNNs and LSTMs, but it's super lightweight. So there are three sort of magic that's going on here. Firstly, as you can see in this diagram, so you can see that the input is ordered. Okay. So you get your input and then you feed it in a certain ordering. So this does not happen in a normal CNN. Okay. So in a normal CNN, if you feed it some input, it's going to just destroy any sort of ordering that we have. But that's not what happens in temporal CNN. The second thing that happens is something known as the use of a dilated kernel. So you can see that compared to a normal CNN where your receptive field is, suppose here it's 3 by 3, a dilated CNN will have a receptive field of almost 1, 2, 3, 4, 5, 6, 7, almost 7 by 7. And that is possible because it has these gaps in the convolutional kernel. Okay. So here you have a higher receptive field but with lower number of parameters, right? So these are apart from this, you also have nonlinear activation as well in the between stacks of convolution layers. So these are like the three magic formulas. So the use of temporal ordering, the use of dilated kernels, and the use of residual blocks for modeling nonlinearity. So these are some special lightweight models that are more suitable for deploying on microcontrollers. Now you can obviously say that, okay, why don't we just, quantize the model or prune the model, which people have been doing for a long time. So my take is, sure, you can do them, but how much will you do? Like, আমরা যদি একটা মডেলকে float থেকে quantize করি, probably it's going to save you like 3.3 to 4x the size, right? But not more than that. So if your model is very big to begin with, then it's very challenging to compress it using quantization and pruning. Okay, so there it's best to use some special architectures like this to develop your model. Okay, so let's take a look at some of the results that we get after combining everything that I presented so far. So here we're doing two things. So in the first graph, we're trying to look at the position of something using neural network. So it takes the IMU data and then it gives you the position. And as you can see, compared to state-of-the-art techniques, our approach is almost 31 to 134x smaller, but our resolution is 1.15x higher. Okay, so using these techniques, actually, sometimes we can even get better accuracy. Similarly, for gesture recognition, you can see that our models, compared to the red state-of-the-art models, whether the red models are by Hatzer, compared to them, our models are almost 740x smaller, but we're getting 3% more accurate models. So if you properly formulate your optimization function, then it's possible to get higher accuracy at smaller models for a lot of different tasks. And I have talked a lot about injecting rules, physics, and making the problem formulation proper. And here you can see what happens if you don't do all those things. So if you don't supply physics, if you don't supply additional data, And if you don't formulate your problem well, then obviously your neural network will have a lot bigger error. Okay. So it's very important that when you are trying to develop applications for IoT, আমরা যদি ডোমেন সম্পর্কে কিছু জানি, like if we know that there are some features that work well, or if we know that there are this phenomena that might help the neural network to improve its error, so we should supply them. Okay, so human knowledge does help a little bit when you are developing things for IoT platforms. And here is one more thing, architectural adaptation. So normally when you do neural architecture search, আমরা মনে করি যে it's going to return the smallest model, but that is not true. So what it is going to do is it's going to return you a model that fits within the device, but if you have more capability, it's going to try to give you bigger models. Okay, the intuition behind that is obviously that bigger models, we think of them as having more accuracy. So Bayesian optimization also thinks something similar. So it learns to give you bigger models if your RAM capacity of your device increases. Like এখানে আমার তিনটা different microcontroller model আছে, and আমি যদি আস্তে আস্তে RAM আর flash বাড়াতে থাকি, then you can see my model is becoming bigger from left to right. Okay, and platform in the loop actually helps. I already told you that there are two ways to estimate RAM, flash, and latency. You can either have the target hardware connected, or you can use some analytical formula. So analytical formula, it can work only so much, right? Like you are bound to make some mistakes. So that's why using real hardware actually makes sense. Like you can see that there is a very large gap in the SRAM uses and the accuracy when you are using proxy versus when you are using real hardware. Okay, so if you want like guaranteed deployment of your model, then it's very important to connect it to your device and then let the algorithm talk to it when doing the neural architecture search. Now there is one more thing which I love to tell everyone, that is how you can transfer your models in the real world to a new domain. So normally what people are going to do is they will train their model on one data set and they will think that, okay, since it has 99% accuracy, it's going to work. But that's not how model development works. Okay, if you deploy it, you will see that its accuracy will drop to 60-70%. So what happens in industry and in academia is when we deploy a model, we try to fine tune it occasionally using on-device learning techniques. And here what we were trying to do is, I showed you that we were doing some localization problem, and then we tried to deploy our model to a robot, and then we saw that, okay, it doesn't work out of the box. Obviously it will not work because our training data was from somewhere else, right? So the model never got the chance to learn the dynamics of the robot itself. So we tried to do transfer learning. What we found out is 1 minute of transfer learning equals 100 minutes of training. Okay, and this is where the value of pre-trained models come in. Okay, so I don't know if you follow machine learning, but you have seen a lot of buzz around GPT-3 and BERT, all this representation learning models. They are not like out of the box, you can't use them, right? So they are not task specific. So what are they? They are like embeddings of all, I don't know, GPT-3 is embedding of all human languages, right? Then you fine tune it to do a certain task. So we propose something similar for for IoT devices too, that we should have this pre-trained model. Suppose we have a pre-trained model for activity detection, okay, that we trained on, I don't know, 100 data sets on millions of people. Then when we finally deploy it to a customer, we'll try to collect some label data for a few minutes, and then we're going to fine tune that pre-trained model. Okay, and in that way we're going to get a lot lower error than if it was even possible to train it from scratch. Okay, so pre-trained models are important. Fine tuning is very important. You cannot just assume that আমার model একটা train করছি অনেক ডাটার উপরে it's going to work. No, that will never happen. You have to do some fine tuning in the field. Okay, now let's take a look at some future directions. So I was talking a lot about fine tuning, and actually it's very important when you are deploying these small models. So what we observed is the models that I showed, like the lightweight RNNs, lightweight CNN LSTMs, lightweight KNNs, and decision trees. So these models have a very hard time, trying to adapt to the new domain because they don't have a lot of parameters, right? So they cannot really learn a lot. So as I said, we have to do on-device personalization, and the way I do it is using transfer learning, which I showed. Problem with transfer learning is you need label data. right? But we don't have access to level data in the field. So how can we even do this? So that's where the value of pre-trained uh, models that operate on unlabeled data come in. Like BERT, GPT-3, they work with unlabeled data, right? So they try to learn a representation of all the information. So can we do something similar for sensor data? Okay. Or even if we do that, then what are some of the good on-device training techniques that we can use? Like there are lots of on-device training techniques. If you read my survey paper, which is the last paper in this footnote, you will see that I have mentioned a lot of on-device learning techniques. Each obviously have their own advantages and disadvantages. So how we can do those? So that's still a challenge that people are exploring. Second challenge that people are exploring is combining data and knowledge. So as I said, that it's very useful to fuse some physics or human information in order to improve the performance. But so far, what I have showed is the neural network physics information that we are fusing. It's not really trainable. So it's not like the neural network is not really aware of like we are not like optimizing it, right? So we just suppose we feed some feature to the neural network and we assume that okay, let the neural network figure it out. But are those things like really, is the loss like really flowing through those human knowledge? So that's where trainable first principle approaches like neurosymbolic reasoning comes in. Okay, so that's one direction that we're working with, like how to properly optimize both human knowledge and neural network jointly. Okay. Last is the problem of backward compatibility. So by backward compatibility, what I mean is, suppose you have trained a model on a certain data set, you have deployed it in the field, it has a very high accuracy. Then you collect some more data in the field and you want to retrain your model on the new data. So you do that and you see that, okay, my accuracy has improved, that's good. But then when you try to see the confusion matrix, you see that in the confusion matrix, the model has started making errors on a different set of inputs. So by that what I mean is you are introducing new errors by trying to increase the accuracy of your model. Okay, so this is something that people don't really expect, but it does happen in the field. So this is known as the problem of backward compatibility. যে আমার যদি নতুন ডেটা থাকে and আমি নতুন ডেটা দিয়ে যদি আমি একটা পুরোনো মডেল ট্রেন করি and then I see that okay, it has higher accuracy, but ওই high accuracy আমরা কি কস্টে পাচ্ছি? We are getting it at the cost of errors on that we have not seen before. Okay, so unseen errors. And this is actually not good when you are deploying these models for like very sensitive applications like health and so forth. So how can we make these models backward compatible? So that is one thing which we are working with as well. Okay, I think I'm out of time and that is all. So if you have any questions, you can ask now.
Thank you. কারো কি কোনো প্রশ্ন আছে? প্রশ্ন থাকলে আমরা হ্যালো
Yeah.
শোনা যাচ্ছে? কারো কোনো প্রশ্ন? আচ্ছা ঠিক আছে। আমি আচ্ছা কারো কোনো প্রশ্ন থাকলে প্রশ্ন করতে পারো, অথবা মানে আমার শুধু কোয়েরি হচ্ছে যে লাস্টে কয়েকটা চ্যালেঞ্জের কথা বলা হয়েছে ফিউচার ডিরেকশনস, ওগুলো কি তুমি এখন কাজ করতেছো নাকি সবগুলো কি করতেছো? অনেক কাজ করতেছো কারণ অলরেডি যতগুলো প্রেজেন্টেশন দিয়েছো মানে স্লাইড দেখলাম সবগুলাতে তোমার একের পর এক পাবলিকেশন, মাশাআল্লাহ, দ্যাটস ওয়ান্ডারফুল। বাট এট দ্য সেম টাইম সবগুলা ফিউচার ডিরেকশন নিয়ে তুমি হ্যান্ডেল করতেছো, দ্যাট ইজ ওয়ান্ডারফুল। আচ্ছা, তো এক কাজ করা যেতে পারে যে এই ফিউচার ওয়ার্ক ডিরেকশন গুলো নিয়ে আমরা রিলেটেড আরো যদি কয়েকজনকে ম্যানেজ করা যায়, আমরা একটা ব্রেইনস্টর্মিং সেশন করতে পারি বেসড অন সাম পেপারস। তো সেরকম হলে আমরা ভবিষ্যতে আরেকটা আয়োজন করতে পারি আর কি। তাহলে যেহেতু কোনো কোয়েশ্চেন নাই, উই ক্যান থ্যাংক আওয়ার স্পিকার। ধন্যবাদ সবাইকে। হোপফুলি উইল মিট ইউ অল অ্যাগেইন। তাহলে ঠিক আছে, তাহলে আজকে আমরা এখানে শেষ করছি। ওকে,
Okay, yep, see you
থ্যাংক
all
ইউ,
later.
থ্যাংক ইউ সবাইকে। So we can leave now. Okay, all the best. Thank you.